Hi, my name is Teresa, and I'm a PhD student in the Dynamics and Neural Systems group at the University of Sydney. So, in this video, I'm going to present a paper that has been recently published in Physical Review Research, a work that I've been doing with my supervisor, Ben Fulcher, on the topic of time reversibility. The work is entitled Identifying Statistical Indicators of Temporal Asymmetry using a data-driven approach. So in this video, I will briefly introduce what time reversibility is in the context of time series analysis. I will introduce the methodology and as described in the paper, and also discuss some of the main outcomes of this study. So intuitively, time irreversibility refers to the ability to distinguish the dynamics of a process that unfolds forward versus backward in time. So usually we don't have much information about the underlying generative process, but what typically we have access to are some single finite realizations from that basically we can use to seek to infer the reversibility of the generative process itself. So, in the time series analysis context, under the stationary assumption, a time series X is said to be reversible if the joint distribution of every subsequence of the time series and of its flipped version are the same. So the flipped version of a time series is nothing else than reversing the order of the data points of the original realization. So estimating joint distributions is typically impractical, especially for real valued, let's say the time series that are realistic. So diverse statistical methods have been developed in order to infer the reversibility from finite data, especially measuring temporal asymmetries. So the aim of this project was to try to understand and identify which are most effective measures for reversibility detection in real data, and also to unify and recapitulate some of the existing methodologies. And the aim would be to try to highlight common understanding in order to enrich a constructive communication across the diverse fields. So to do so, we need two ingredients, the comprehensive set of systems and a comprehensive range of summary statistics to test. This is what is represented in figure 1 of the paper. Panel A shows a summary of the time series generated from processes that we subdivided into 6 families. And we wanted a sufficiently diverse set of processes to capture a wide range of dynamical signatures in which irreversibility could manifest. In panel B, there is a summary of the highly comparative time series analysis approach, in short HCTSA, applied for the reversibility problem. So HCTSA proposes a shift in perspective, where rather than considering a time series as a signal that evolves in time, it characterizes it in terms of more than 6,000 features. So applying this to the reversibility problem means having our forward time series and our backward time series. Then we transform them into a set of features. And we say that a summary, that is the absolute feature difference, is an informative measure if it is 0 for the time series generated by the reversible processes and non-zero for the irreversible ones. And so when we end up having these 6,000 measures, of course, we don't know which are the good and the bad. And so we assign each feature a score, and specifically the classification accuracy of a first nearest neighbor classifier. This is represented in the distribution of the accuracies for the features in this in panel A. We see the majority of statistics are insensitive to reversibility, but there is a set of features that instead are sensitive to reversibility. And so the distribution of the feature differences are reported in in the panel B for a subset of these statistics. And so we could, in short, say that we could recapitulate the effectiveness of established statistics. And this is represented by the fact that the distribution is close to zero for reversible and is much wider for the irreversible ones. We could suggest also some modifications of classical measures that worked well, and also show methods for irreversibility detection that have not been commonly used to our knowledge. For example, a forecasting measure such as the mean absolute error of an AR2 predictor. The last highlight I want to show is that we have identified statistical signatures of irreversibility that are highly process dependent. And this is a consequence of the breadth of the comparison, both in the systems and in the statistics that have been developed and used. So thanks to this, we could demonstrate that there is no general fixed best statistic that is effective for detecting irreversibility across all the systems, but rather that each statistic captures a specific manifestation of irreversibility. And this is shown, for example, in panel B and C, where the generalized correlation can capture the asymmetry in the autoregressive process, but not in the logistic, that is still an irreversible process. And while the vice versa is true for this symbolic measure. So also the HCTSA library is sufficiently comprehensive to identify an accurate measure and for capturing this specific asymmetry across the simulated processes. So what we shown is that we could always find a statistic that works for a given process, but also that for each feature, we always find at least the one process for which it fails to detect the irreversibility. And that is what is represented in panel D. So to wrap up some final conclusions, we represented a unified organization in this paper of the statistical approaches. And the data-driven method that we used, I revealed the diversity of the types of existing statistics. Also, the fact that thanks to the breadth of the method, we could identify an inter-process variation, and that no single fixed summary statistic fully captures irreversibility itself. But since this concept is a multifaceted one, we suggest that to tailor the summary statistic to the specific irreversibility of the process. So thanks for the interest in this work, and also thanks to my research group.